In this video, we're going to talk more about plotting surfaces in 3D space. In particular, we are plotting cylinders and quadric surfaces. So we'll start off with cylinders, which is the simpler of both of them. So a cylinder is a 2D curve which is stretched infinitely across an axis. So if you're presented with the equation and you only see two of the three variables, it could be x and y and z, or x and z, then you have a cylinder. So we'll start with the circular cylinder, which is what most are familiar with. So we just think of the 2D equation for a circle. Now we could use any of the two variables. I'm just going to use x and y to start with. So the circle equation with x and y is x squared plus y squared equals r squared, in which r is the radius. So let's say we wanted to graph a circle with a radius of 1. Our equation is x squared plus y squared equals 1. We know how to plot this in 2D. We can start with that. So with a radius of 1, we'll go out 1 and negative 1 on both the x and y axis. And this is our circle. But what happens if we take this equation and we want to plot it in 3D space? So we can plot x squared plus y squared equals 1 on the xy plane of the 3D graph. So here's x equals to 1, x is equal to negative 1, y is equal to 1, and y is equal to negative 1. And we can make out a circle like this. Now, notice how the variable z is not in the equation. This means that z can take on any value, and z will not alter this circle at all if you go up and down the z-axis. So what you really have is infinite circles spanning up and down. We can draw the same circle above and below to demonstrate the idea that it doesn't matter where you are on the z, you'll still get plots of x squared plus y squared equals 1, which is the same circle. It's not getting smaller, it's not getting bigger, it's not being changed in any way. If you were to look top down, you would see the same cross section of the circle. And that is a graph of a circular cylinder in 3D. I'll also include a visual from a digital grapher so we can get a better idea of it. When we are referring to cylinders in Calculus 3, we don't necessarily mean it has to be the circular cylinder that we saw earlier. It just means that every time we see an equation with two variables, there's going to be a missing variable, and we're just going to have a 2D graph that's going to be stretched along the missing variable. So let's take a look at an elliptic cylinder. We start with the cross section of an ellipse. So the ellipse equation is x squared over a squared plus y squared over b squared equals 1. And again, it doesn't necessarily have to be x and y, it can be any of the two variables. Let's say we wanted to graph y squared over 1 plus z squared over 4 equals 1. We can start with a 2D trace. So let's plot this ellipse equation on a two-dimensional graph first. So we can have the y-axis here and the z-axis here. So this means that 1 would be a squared and 4 would be b squared. The bigger coefficient represents the semi-major axis and the smaller coefficient represents the semi-minor axis. Since we have a squared equals 1, a would be 1 and negative 1, and this would be along the y-axis. And then b squared equals 4, so that means b is 2 and negative 2. And that's for the z. This is how we get our ellipse. Now let's go to the 3D graph. So we can take this ellipse and we can plot it along the yz plane. And for this equation, y squared over 1 plus z squared over 4 equals 1, x is our missing variable. So this means that we'll have this ellipse span forward and backward, in which x will not alter it, because it does not matter what value of x we have, we will still have y and z variables forming this ellipse. And to do so, we can make a copy of this ellipse, and we can move it forward and back. If you want, you can draw lines that are parallel to the x-axis to guide you when drawing the copies of the ellipse. So this first line right here is going to be representing the bottom point. And we can also do the same for the top. So we could have something that looks like this. If we have the ellipse at some negative x value, then we can do the same thing for when x has a positive value. And then we can also draw a point on the right of the ellipse and connect those as well. And we're going to do the same on a point on the left of the ellipse. Dashed line representing the back of it. And this should be sufficient in representing your elliptic cylinder. We can also have a parabolic cylinder. And you could use any of the two variables to come up with an equation of a parabola. For example, z equals y squared on a two-dimensional graph where we have y is the horizontal axis and z is the vertical axis. We know that we have a parabola facing upwards if we have the coefficient of positive 1. Now let's draw this on the 3D graph. So let's draw a parabola on the yz plane. So again, x is our missing variable, which means it does not affect this parabola. Going forward and back along the x-axis, we're going to have copies of this. So we can place the same parabola somewhere along the negative axis, and we can place one on a point along the positive axis, and then we can make a line that connects the top left of them, and a line that connects the top right of them. We can even have a hyperbolic cylinder where we have an equation of hyperbola. Let's say we wanted to plot y squared over 1 minus x squared over 1 equals 1. We can start with the 2D if you want. And if we want to plot this on 3D, we can start by plotting the hyperbola along the xy plane. And then z is the missing variable from this, so we have a hyperbola spanning up and down the z-axis. Just make a copy of this and lift it up a little bit. And then we could connect the ends of it. So essentially you can think of the hyperbola looking like ribbon in 3D with that infinitely goes up and down along the z-axis. We can also connect where it bends. And usually to represent edges that are behind another surface, we would use dashed lines. Again, cylinders in Calculus 3 are just plots using two variables, so we have a 2D graph, and we're just stretching it along the variable that is not present. So we can even have something that is x equals cosine of y. This is also a cylinder. So if we look at the 3D graph, and this means that the maximum and minimum value of x is going to be 1 and negative 1. And we can draw the cosine. And this cosine is going to be the same regardless of what the z value is. So we'll span this infinitely along the z-axis. To show this visually, we can just lift this above it or below the curve. So now we can connect the edges. Now we are going to talk about quadric surfaces. Quadric surfaces are second-degree equations in 3 dimensions. So we can have x squared, y squared, z squared. But first let's recall the conic sections in 2 dimensions, where we can have circles, ellipses, parabolas, and hyperbolas. So if we square x and y terms in 2 dimensions, we get these types of graphs. When we talk about quadric surfaces in 3D now, the cross sections may include some of these. So given that the conic sections from 2 dimensions have squared x terms and squared y terms, they can fall under this general formula. So your ax squared and your cy squared are the second degree terms, the bxy is a mixed term, and then dx and the ey, that's the linear transformation, and then we have the constant f. So for quadric surfaces in 3D, we have the variable z, and if we have combinations of it in first order and second order, we can have this general equation for quadric surfaces. So we have ax squared plus by squared plus cz squared plus dxy plus eyz plus fxz plus gx plus hy plus iz plus j equals 0. So again, x, y, and z are our variables. The letters a through I are all coefficients, and j by itself is a constant. Ax squared plus by squared plus cz squared is the second order terms. Then we have our mixed terms, dxy plus eyz plus fxz. These are the rotations for the quadric surfaces. And then gx plus hy plus iz, these are linear terms. They control the shifting left, right, up, down, and forwards and backwards. So to start learning quadric surfaces, we're going to simplify this equation, and we're just going to worry about ax squared plus by squared plus cz squared plus dz equals e. So some examples of quadric surfaces are ellipsoids, hyperboloids, cones, elliptical paraboloids, and hyperbolic paraboloids. And as you may have noticed, they somehow have similar names as the conic sections learned earlier. So first, we are going to look at an ellipsoid. It has the equation in standard form of x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Now, generally, there are different ways. If given a quadric surface equation, you can tell what type it is. In this case, for an ellipsoid, all the variables are squared, all the variable terms are positive, and there's a constant on the other side of the equation. So let's do an example where we want to plot 4x squared plus y squared plus 4z squared equals 4 in a 3D graph. So first, let's put this in standard form. You don't always have to do this, but it is easier to graph and see what's going on. So if we divide everything by 4, we're left with the equation x squared over 1 plus y squared over 4 plus z squared over 1 equals 1. So now we have the ellipsoid equation in standard form. Now, the way to graph quadric surfaces is to cover up one of the variables so we can have the traces along each plane. So basically, if we cover up one of the variables, let's say z, we are left with the equation x squared over 1 plus y squared over 4 equals 1. Now, this equation, we know what it looks like in 2 dimensions. This is just an ellipse equation. So if we plug in 0 for z, we are looking on the xy plane. So let's say we want to plot this 2-dimensional graph if we have x along the horizontal axis and y along the vertical axis. We know that 1 equals a squared, so a equals plus or minus 1, and b squared equals 4, so b equals plus or minus 2. And we can just plot an ellipse. So now I'm going to do the same thing for the other variables. Let's say we wanted to cover up y this time and plug in a 0 for y. We now are on the xz plane, and we have this equation, x squared over 1 plus z squared over 1 equals 1. Well, since the coefficients are on the same, we could just multiply those to the other side if we want, and it's basically a circle equation, but it's still an ellipse. Now let's cover up the x, and if we plug in a 0 for x, we are on the yz plane, and we're left with the equation y squared over 4 plus z squared over 1 equals 1. And this is another ellipse equation. So if we covered up each variable and plotted the equation for the other two variables, we see sketches of ellipses. So let's go to a 3D graph and try to plot this. To graph the ellipsoid, we can take a look at the three traces and we can place those on the planes so we can piece it together. So we'll start with the xy plane, which is the first trace we got. So x runs from -1 to 1, and y runs from 2 to -2. And we have an ellipse here. So on the xy floor when z equals to 0, that's basically this right here. Next, we're going to put the xz trace on. Both x and z run from -1 to 1. So that dashed line represents the second trace, which is along the xz plane. That ellipse is precisely a circle because x and z has the same coefficient. And before I begin the last one, I'm just going to turn the first trace into a dashed line as well. Usually dashed lines represent that an edge is going behind the surface. So now we're on the yz trace, and we plot this when x equals 0, which is along the yz plane. And again, y ranges from -2 to 2, and z ranges from -1 to 1. So now, using the three traces, we plotted an ellipsoid on the graph. You can think of an ellipsoid as an elongated sphere, the same way an ellipse is an elongated circle, if at least one of the coefficients are different from the others. One thing I do want to edit real quick is the constant doesn't have to necessarily be on the other side of the equation to start with. If you're given an equation and you want to identify it's an ellipsoid, it may be on the side with all the variables, and you just have to subtract or add it to the other side. So I'll just leave the third point as constant. So from the ellipsoid equation, if we change one of the variable terms to a minus sign, we then get a hyperboloid of one sheet. So it doesn't matter which term it's negative. If you just have one of the terms negative, then you'll have a hyperboloid of one sheet. So to identify a hyperboloid of one sheet, you'll see that all variables are squared, and two of the variable terms are positive, and one of the variable terms are negative, and you have a constant. And this would be the standard form of the equation. So let's say we wanted to plot 4x squared plus y squared minus z squared equals 4. Again, any of the variables could have that negative sign. In this case, it's just z. So first, let's put it in standard form. This means a squared is 1, so a equals plus or minus 1, b equals plus or minus 2, and c equals plus or minus 2. Again, when plotting quadric surfaces, we're going to look at the three traces first. For the xy trace, we cover up the z term. We are left with x squared over 1 plus y squared over 4 equals 1. This is an ellipse equation, and we know how to plot that. So that's our xy trace. Now let's cover up the y, and we're left with the x and z terms, and we have x squared over 1 minus z squared over 4 equals 1. If you remember, this is an equation of a hyperbola. So since z is our vertical axis, the equation for the asymptotes are going to be z equals, and it's going to be as a function of x, plus or minus the slope, which is going to be the coefficient, the square root of the coefficient under z over the square root of the coefficient under x. So this is going to be plus or minus 2 over 1 times x, or z equals plus or minus 2x. So this is going to be the asymptotes for the hyperbola. Next, we can get the x-intercepts, where if we plug in a 0 for z, we're left with x equals plus or minus 1. So we have a point here and a point here. Hyperbola looks like this. Now if we cover up the x term and we're left with y and z, we'll also get another hyperbola equation. Y squared over 4 minus z squared over 4 equals 1. Alright, so z is our vertical axis again, so our asymptotes are z equals plus or minus 1x. Getting the y-intercepts by plugging in 0 for z, we will have y squared over 4 equals 1, or y squared equals 4, and y equals plus or minus 2. Now we can plot it on a 3D graph. First, along the xy plane, we have an ellipse. So if you want, you can take the xz trace and the yz trace to plot the hyperbolas along the sides. They're going to be connected to these 4 points. So something else you can do is you can plug in another value for z, and we'll make out another ellipse. So let's write down the equation again. So to get our first trace, the xy trace, we plugged in a 0 for z. If we plug in another value for z, let's say we want to plug in a 2, we will get a different ellipse. So let's move the constants to the other side, and we can have the equation as x squared over 1 plus y squared over 4 equals 2 squared is a 4, and a 4 divided by 4 is a 1. So if we add 1 to the other side, we'll have a 2. And then we can divide everything by 2 to get it in standard form. So this means for at z equals 2, I'm just going to scale largely on the z-axis since it's easier to space it apart. So from this equation, this means that a equals plus or minus rad 2 and b equals plus or minus rad 8. So that means that up here at z equals 2, we have a bigger ellipse. Y is plus or minus rad 8, and these x values are radical 2 and negative radical 2. And then you will notice that since z is a square term, this same ellipse also applies for when z is negative 2. And now with these extra 2 ellipses for reference, we have an easier time sketching the hyperbolas. So we'll start with the yz hyperbola. We just connect the outer points. So now for the xz hyperbola, which is the second trace, I'm going to use green to differentiate. So we have a front point here, and a point here. We're just connecting these. And then we also have our back points. And that is how you graph a hyperboloid of one sheet. If we take the equation for a hyperboloid of one sheet and we add another negative variable term to it, we're going to have the equation for a hyperboloid of two sheets. So a hyperboloid of two sheets has all its variables squared. It has one positive variable term and two negative variable terms, and it has a constant. Let's say we wanted to graph the equation 16x squared minus y squared minus 4z squared equals 16. We can get this into standard form by dividing everything by 16. And like before, we can try to plot 3 traces for each plane. So we'll start with the xy plane. This is when z equals 0. If we plug in a 0 for z, we're left with x squared over 1 minus y squared over 16 equals 1. So this is a hyperbola. We can do the same thing for the xz plane when y is set to 0. We're left with x squared over 1 minus z squared over 4 equals 1. And this is also a hyperbola. Now let's take a look at the yz plane. If we plug in a 0 for x, we have y squared over 16 negative y squared over 16 minus z squared over 4 equals 1. And if you'll notice, there is no numbers for y and z that can make this part of the equation equal to 1. Because this part can either be 0 if you plug in 0 for y and z, or it will be some negative number. So that means there will be no points along the yz plane. So if we wanted to take a look at a trace for y and z, we should plug in another value instead of x equals 0. This also makes sense for the xy trace and the xz trace, because if you look, there is no plot or points when x is equal to 0. So there are points that exist on the surface when x is 1 or greater, or when x is negative 1 or lesser. This means that we should plug in values in which the absolute value of x is greater than 1 to get a yz trace. So let's say we want to plug in 2 for x. We have the equation 2 squared over 1 minus y squared over 16 minus z squared over 4 equals 1. Rearranging some terms and simplifying the equation, we have y squared over 48 plus z squared over 12 equals 1 when x equals to 2. So this is an equation of ellipse. Cross sections of the surface parallel to the yz plane, if it's greater than the absolute value of 1, would give ellipses. 3D plot. Okay, let's start with the xy trace. Now the xz trace. And then for the yz trace, you'll get ellipses as the cross section when the absolute value of x is greater than 1. So this is the graph for the hyperboloid of two sheets. The next quadric surface is an elliptical cone. For its equation, all the variables are squared again. There is one variable term on the other side of the equation, and all terms are positive, and there's no constant. So let's say we want to plot this following equation. 4x squared plus 9y squared minus 9z squared equals 0. So to get it in the form of the equation above, we can get the 9z squared term to the other side, and then we can divide everything by 36, since 4 and 9 are both factors of it. Now let's do the traces. We'll start off with the xy plane, and this is when z is equal to 0. So by blocking out z, we have this equation, x squared over 9 plus y squared over 4 equals 0. When z is set to 0, the only way for this equation to be valid is when both x and y are also equal to 0. This means we have a point at 0, 0, 0. If we look on the xz plane, this is when y is set equal to 0, and we have the equation x squared over 9 equals z squared over 4. We can cross multiply, and then we can isolate for the variable which has the vertical axis, which is z in this case. And then z equals plus or minus 2/3 x. And that's just a linear plot. Now let's take a look on the yz plane. This is when x is equal to 0, and plugging in a 0 for x, we have y squared over 4 equals z squared over 4. We could cancel out the 4's on the denominator on both sides, and we're left with, if we isolate for z again, z equals plus or minus the square root of y squared, or z equals plus or minus the absolute value of y. And if we wanted to take a look at another xy trace that is not the point, we can just choose any value of z that is not 0. So let's say we have z equals to 2. We would have x squared over 9 plus y squared over 4 equals 2 squared over 4. This then gives us x squared over 9 plus y squared over 4 equals 1. And this is an ellipse. I will also label the others. Now we can plot it on a 3D graph. So first of all, when z equals 0, x and y have to be 0, so we have a point at 0, 0, 0. Next, we can draw the trace of the ellipse when z equals 2. I'm going to scale the axes differently so we can have a better picture. The trace of the ellipse at z equals 2 is also the same at z equals negative 2 because the z term is squared. Now we can put on the xz trace. And then the yz trace I'm going to do in green so we can differentiate the lines. Keep in mind, all the lines for the xz trace and the yz trace all pass through the origin. And this is the sketch for an elliptical cone. Next up we have an elliptical paraboloid. You can identify the equation of an elliptical paraboloid if you see that two of the variables are squared, and when they're placed on the same side of the equation, they have the same side. They have the same sign. And the other variable is a first order, and it's usually placed on the other side of the equation, and there are no constants. Let's say we have this equation, 4x squared plus y squared minus 4z equals 0. To get it in the form as above, we can move the z term to the other side since it's the first order term. And then we could divide everything by 4. Like before, we can go ahead and find the traces. So let's start with the xy trace. This is when z is set equal to 0 for the xy plane. If we cover the z term, we have x squared over 1 plus y squared over 4 equals 0. The only way this equation can be true is if both x and y also equal 0. So this means we have a point at the origin. Since that xy trace gave us a point, we can choose another value of z. Let's say z equals 1. The equation we have is now x squared over 1 plus y squared over 4 equals 1. And this is the equation for an ellipse. Next, let's look at the xz trace. We can set y equals to 0 for the xz plane. So we have x squared over 1 equals z over 1. We can write this as z equals x squared, and this is the equation of a parabola. And now for the yz trace, we can set x equals to 0, and then we are left with y squared over 4 equals z over 1, and we could say z equals 1/4 times y squared. This is also a parabola. Now we can go on the 3D graph, and we know that we have a point at 0, 0, 0. Next, we can go to z equals 1, and we can place the ellipse there. I'm going to scale it differently so that we have a better picture. Next, we can put on the yz trace. And then we have the xz trace, which I'm going to put in green. And this is an elliptical paraboloid. And finally, we have the hyperbolic paraboloid. You can identify the equation of a hyperbolic paraboloid if you see the second order terms, when placed on the same side of the equation, have opposite signs. The other variable is in a first order term, and is usually placed on the other side of the equation. And there's no constant in this one either. So let's say we have the following equation. Negative 2y squared plus 6x squared plus 12z equals 0. First, we can move the first order term to the other side of the equation. Next, we can get the coefficients into the denominator. 2, 6, and 12 are all factors of 12, so we can divide the equation by 12. And finally, it's helpful to get the z term into positive, so we can divide everything by a negative 1. So we have y squared over 6 minus x squared over 2 equals z. So again, we can do the traces. We'll start off with the xy trace, and we'll start on the xy plane by setting z equals to 0. Plugging in a 0 for z gives us y squared over 6 minus x squared over 2 equals 0. We can try isolating for y, since y is the vertical axis. After simplifying, we get y equals plus or minus the square root of 3 times x. And these are lines. If we do another xy trace, and we set z to something greater than 0, let's say z equals 1, we will have this equation. Y squared over 6 minus x squared over 2 equals 1. This is an equation for a hyperbola, and has the asymptotes y equals plus minus square root of 6 over 2 times x, or y equals plus minus square root of 3 times x. Something I want to point out that is interesting is that if you plug in a negative value for z, let's say z equals negative 1, we will have this equation, y squared over 6 minus x squared over 2 equals negative 1. So if you multiply everything by negative 1 so that this can be positive, we will have negative y squared over 6 plus x squared over 2 equals 1. And this is also a hyperbola, but if you notice this time, the x has a positive and the y has a negative. So this means that this hyperbola will open up towards the x-axis. So let's do the xz trace. If we look at the xz plane, y equals 0. Plugging in a 0 for y gives us negative x squared over 2 equals z. You can also say z equals negative 1/2 times x squared. And this is a parabola. And then for the yz trace, if we look on the yz plane, x is equal to 0. The equation we're left with is y squared over 6 equals z, which means z equals 1/6 times y squared. Now let's plot it on the 3D graph. We mainly use the parabolas when plotting the surface. So we'll start with the yz trace. Next, I'm going to use green to graph the xz trace. Let's take a look at this equation over here again. Y squared over 6 minus x squared over 2 equals z. If we talk in terms of yz traces again, which is how we got that blue parabola, no matter what value we plug in for x, we'll always get z equals y squared over 6, that shape of the parabola. The negative x squared over 2 term, that just shifts the parabola up and down. So that means for any value of x on that surface, we should still see the same shape of the parabola. Since this term isn't changing for changing values of x, the parabola should not stretch or compress. So this means at this point and at this point, we can put the vertex of that same blue parabola. The same idea for this equation can be applied when looking at the xz trace. If we plug in any value for y, we will still have z equals negative 1/2 times x squared. This will not stretch or compress again because the only thing that is changing is the y squared over 6 term, which shifts it. Since these 3 points are on the surface that have the same y value, that same green parabola can be used to connect those 3 points. The same green parabola can be used to connect these 3 points since they have the same y value. So this is the graph of a hyperbolic paraboloid. It is a saddle surface, and you can think of its shape like a Pringle chip. To review, we can graph quadric surfaces by looking at the xy, yz, and xz traces and piecing together the cross-sections. So for an ellipsoid, all 3 cross-sections will give an ellipse. For the hyperboloid of one sheet, 2 of the cross-sections will be hyperbolas, and the other cross-section is going to be an ellipse. The axis that the ellipse wraps around is the term with a negative in it. So in our example, we had a negative z term. The ellipses get bigger when the values of z get further away from the origin. For the cross-sections of a hyperboloid of 2 sheets, 2 of them were hyperbolas, and one of them was an ellipse. And in this case, these 2 hyperbolas share 2 vertices. The axis that the ellipse wraps itself around is going to be the variable term that is positive. In our example, we had the ellipse wrapping around the x-axis, so we had a positive x term, and the other 2 terms were negative. For an elliptical cone, we have 2 sets of 2 lines. All 4 of those lines intersect at the origin. And in the equation, 2 of the variable terms are on the same side, and there's 1 variable term by itself. The variable term by itself in our example is z, so when z equals 0, we'll have a point at the origin. If z was some other value, we'll have an ellipse wrapping around the z-axis. And the traces of the ellipse get bigger the further z is away from the origin. For an elliptical paraboloid, 2 of the traces are parabolas, and both those parabolas intersect at a point. That point is there when the variable that is not squared, in our case z, was set equal to 0. On the side of the equation with the squared variables, they both need to have the same sign, either both positive or both negative. In our example, they were both positive, so if our isolated variable z was set to some positive number, we'll have a trace of an ellipse. This ellipse wraps around the z-axis. In our equation, z was the variable that was not squared. And finally, for the hyperbolic paraboloid, we had 2 parabolas, and they both intersect at a point. The other trace, given by the 2 variables that were squared, give lines that intersect at the same point that the 2 parabolas intersected at. We get those lines when our other variable z was set equal to 0, and if z was set to some other value, we'll get a hyperbola. And that sums up the cross-sections we can have from these quadric surfaces.